Please find your seats. Okay, good evening. Welcome to the IMA Public Lecture. My name is Fadil Santosa. I'm the director of the Institute for Mathematics and its Application, the IMA. I'm pleased to introduce our speaker for tonight. Jill Pipher is professor of mathematics at Brown University and is the founding director of a new institute called Institute for Computational and Experimental Research in Mathematics, or ICERM, as she calls it. Like the IMA, her institute is a National Science Foundation Math Science Research Institute. Professor Pipher received her PhD in mathematics from UCLA in 1985. She was at the University of Chicago for 5 years before joining the faculty at Brown University as associate professor. At Brown, she was appointed professor and then in 1994, and also served for 3 years as the chair of the math department. Professor Pipher is well known for her mathematical contribution in the areas of harmonic analysis, partial differential equations, and also cryptography, a subject that she'll talk about today. Her awards include an NSF Presidential Young Investigator Award, an Alfred P. Sloan Foundation Fellowship. Another unusual aspect of her career is that she jointly holds 3 patents on cryptography, U.S. patents on cryptography, and in 1996, with 3 other members of faculty members in her math department, they started a company called NTRU Cryptosystems. And the company recently merged with Security Innovation in 2009. She's also the president of the Association for Women in Mathematics. So without further ado, Jill Pipher.
Thank you. Thanks a lot, Fadil, for that wonderful introduction. It's a real honor for me to be here. The IMA is a tremendous resource in the math community, but also in the general public, as I can see here. And I'm just really thrilled to be here. I've been looking forward to this night for a while. So let's start with some big questions. So these are the questions I'd like to talk about tonight. First, how can I send an encrypted message to my friend? Though when you have a friend you want to send some coded message to, you figure that you can communicate a secret aside. That's different from the question of how can I send an encrypted message to a stranger, to someone I've never talked to before. How do I know if an encryption system is secure, is unbreakable? And can I make a lot of money, or at least earn a good living in cryptography? And we'll see that the answer to the first question is maybe, maybe not. But the answer to the second question is definitely yes. Some of the political and philosophical issues in the subject of cryptography are quite big. So public key cryptography, which is eventually the subject I want to get to tonight, is essential for commerce, for trusted authentication. It's vital to control online fraud. But then individuals want to keep secrets, and that runs counter to the government's desire to be able to detect secrets and to have information that it deems important for national security. And that's a big story in cryptography. And finally, can we really control the availability of cryptographic methods? And do we need to? The history of cryptography naturally breaks up into two sections. One is sort of from the Stone Age to the 1970s. And cryptography in this period was fairly simple. Coded messages involve scrambling. You just take your letters and you convert them perhaps to numbers, 26 letters in the alphabet, and or you might convert them to sequences of zeros and ones, bits. And the scrambling, which is the code, can be done by hand or it can be done by machine, as it was later. And I'm sure most of you have heard of the Enigma machine that was so important in World War II. So let me give you an example, a simple example of how to send a coded message, which you're probably familiar with from childhood coded messages. Okay, so let's call the letters A is 1, B is 2, etc. And now our simple encoding is going to look like this. We're going to code a message by shifting every letter by 5. Not too complicated. So A would be replaced by F, and B is replaced by G, and so forth. So there's an example of a message written in this code. Got it? No? Okay. You'll see it again. There's a clue here. This is called the Caesar cipher. It's just a simple shift of letters. And it's pretty easy to do. It's also pretty easy to undo if you know what the shift was. If someone says, I shifted by 5, you would say, okay, I can decode because I just, unshift by 5. So the security of this cipher, it rests in the fact that the protocol, which shift you did, is a secret. And besides, at the time it was invented, few people were reading anyway. But suppose you know that the protocol involved some sort of shift. Then you could say, well, I don't know which one, but I could guess. Let me try this shift by 1. Let me try shift by 2. You just go through the possibilities. There's only 26 of them. Eventually, that will make sense. There's that message again. Okay, well, move on. Okay, so that's the Caesar cipher. But technology advances because it's really not that hard to break if that's the only one that you're using and you have to just guess which one it is. And one of the first ways of constructing, so the question is, how can you construct a cryptosystem, a message of coding and decoding that's simple enough to use, like the Caesar cipher was pretty simple, but it's complicated enough so that it's hard to find the secret key. That's the essential problem. So here's a first try at that. It's called the Vigenère cipher. So here's an example of how it works. You pick a word, a simple word like cab, C-A-B. And this is a key, this word cab, and it encodes a method for sending coded messages. And the way that works is this. The protocol is we're first going to divide the messages into blocks of 3. Where did 3 come from? The word has 3 letters. Oh, and by the way, I do encourage you to jump in with questions, comments, so don't stay silent. Okay, so we divide our message into blocks of 3, and the first letter of each block we're going to shift by 3. Why 3 there? Why that 3? Because there's a C there, and C is the third letter of the alphabet, so the first one we're going to shift by 3, and then the second in our block we're going to shift by 1, and the third by 2. And then we're going to go back to the beginning. The next block of 3 will shift by 3, 1, 2. So that makes things pretty complicated, right? Because let's look at the security analysis of this cipher. Because, decryption is just as easy as encryption. You just reverse this process. So there's the thing that you're starting to notice about the ciphers that I'm describing now is that encryption and decryption are just exact opposites of one another. You just do exactly what you did to decrypt, but you just do it in reverse. Okay, let's analyze the security of this. Well, there are lots of words. So that's good. That makes it a lot harder to guess. And in fact, we don't have to use just 3-letter words. We could use much longer words. We could even use sentences as our keys. So there's too many to try all possibilities, as you can see, because you can make pass your key any length you want, even a page in a book. But maybe there's a sneakier way to break this code. So just because you can't guess all the possibilities doesn't mean that there isn't another way to try to decode. So that brings us back or up in time to 1948 and Shannon's communication theory. So this was a groundbreaking paper in that it defined certain quantities that you really wanted to be able to talk about, like secrecy and security. And one of the things that was was quantified in this paper was one method of attacking this code. It has to do with the frequency that letters occur in a natural language. So when you're seeing a scrambled message, you might notice that one, say, R, appears many times. Well, if the R appears many times, then maybe it's one of the more frequently, maybe it stands for one of the more frequently occurring letters in the English language. So you might make a guess that R stands for E. And so forth. And this frequency analysis can be carried out on a fairly sophisticated way. And so this is really one way of attacking codes that involve simple shifts and replacing letters by other letters. Shannon quantified the concept that we all intuitively know. There are redundancies in natural language. Can you read that sentence, which has no vowels? Yeah, you can, because you don't actually need every single letter of the sentence to actually be able to read it. And this characterization of the redundancy of language, he called entropy. And Shannon defined the entropy of a natural language and the concept of perfect secrecy. And he gave a definition of what it meant for an encryption system to be secure. Let me give you, I won't go into the definition, but let me give you an example of a cryptosystem, of the idea of a cryptosystem that's perfectly secure, that can't be broken. It's a pretty simple, actually, idea. So it's called a one-time pad, and in this cryptosystem, the ciphertext, which is another name for the encrypted message, can be provably gives no information about what the original message is. In other words, if you see the ciphertext, there is no way of guessing what the original message was. That's perfect secrecy. So in order to achieve that, however, the key, like that word cab, has to be completely random and used only once. So this is not a very practical crypto system. It's not going to help you send your credit card securely across internet to Amazon.com, because you're only going to be able to use that crypto system, that key, once. And the theoretical advantage, the perfect security, is offset by this big practical disadvantage. The key has to be as long as the message, and it has to be randomly generated, and it has to be securely exchanged between two people. You have to be able to tell the person, I'm using this key, because otherwise nobody can decode. Let me show you how it works. Let me give you a simple example. So the message, in this case, is just going to be a string of zeros and ones. It might stand for letters, or it might be a clue about something else, but it's just a string of zeros and ones. And here's how you encrypt. If you don't know XOR, forget it, and here's the example. So up here I have a string of zeros and ones. That's my message. That's the message I'm going to send to you, and I'm going to use this key. This is my key. And how do I get the encryption? Well, the encryption is 0 plus 1 gives me 1. 1 plus 1 gives me back to 0. 0 plus 0 always adds to 0. So that's the way that operation works. So if you give me a message, I will give you back this encryption message. And now, why is it perfectly secure? Suppose I see a 0 down here. Well, that means that this, I can't really tell what was in the message, right? The message could be a 1, and then the key could be a 1. Or I could see a 0, and the message could be a 0, and the key could be a 0. So just looking at the output line, I can't tell you what the input line is if I don't know the key. So that's why it's secure. Okay, so this is not what happens with modern ciphers. Modern ciphers involve practical keys. And practical keys are a lot shorter than the message. But the length of a key, like our CAB example, 3 letters, you might even be able to guess that if you knew that the keys were only 3 letters long. The length of a key determines how hard it is to break. Length determines strength. (128-bit) keys are the norm today, with 200. That means 128 zeros and ones. 256-bit keys for sensitive data. And if there are a certain number of bits, then there are 2 that many possibilities for a key, because you could put zeros or ones in each one of those slots. And so you'd have 2 times 2 times 2, etc. possibilities. Okay, so we have this problem. We'd like to be able to communicate securely, even with a friend. But we still have to exchange a key. I still have to give you the secret key, or you can't decode my messages. So the concept of secure key exchange is a really wild one. Here's the idea. Let's introduce our characters. Our characters are Alice and Bob. They're typical characters in the cryptography story. Later we'll bring in Eve. Eve is the eavesdropper. I didn't make this up. So Alice and Bob need to exchange a secret key so they can send each other secret messages. But essentially they can only do this across a crowded room. And they can only do this by shouting to one another. So Alice and Bob have to shout to one another across a crowded room. And that means that, and at the end of that time, they're going to walk away with some information that all the people in the room who heard that shouting don't have. And that's the crazy thing that this mathematics enables them to do. So, in the mid-1970s, Whitfield Diffie was asking this question: how can we make this happen? How can we leave out the part where Alice and Bob meet in secret? How can we actually get them to exchange a key by shouting across a crowded room? In other words, what information can Alice shout to Bob and Bob shout to Alice so that at the end of the day they walk away with a secret that nobody else has? So there's a fundamentally new idea. And that fundamentally new idea is what's behind public key cryptography. So that's different from this scrambling ciphers and things that involve sharing a key. It's a really different concept. And that's what enables you to get on the internet and communicate securely with your bank, with your credit card, to purchase something online. That's what makes it possible to make these secure communications. You are communicating to a stranger, that internet manufacturer. You're communicating to a stranger, and you've never shared a secret with that stranger before. Now, you may not realize it, but your computer is doing this encryption automatically. And only Amazon.com is able to decrypt. So, in 1976, Diffie and Hellman published a foundational paper in the subject of cryptography, and this is where public key cryptography enters. And they begin their paper with some remarkable words for a mathematics paper. We stand today on the brink of a revolution in cryptography. And that word revolution was really meant, can really be taken in a couple of senses. because there is an actual revolutionary aspect of public key cryptography enabling mass secure communication. And the government also recognized this as revolutionary, and we'll get to that story in a minute. Now, in this paper, Diffie and Hellman invented the concept of public key cryptography, but they could not give an example of a public key cryptosystem. They said, imagine this. And they gave the outlines for how it might work, but they were missing the part where you actually had an example of one, and that was to come later. They described the idea, the concept of digital signatures, and how you could get that if you could solve this public key cryptography problem. And they gave an algorithm for that secure key exchange. Remember I said Alice and Bob want to share a secret by shouting across a room? They actually gave an algorithm for that, for how to do that, the mathematical idea for that. And it's still used today for secure key exchange. So here's the problem that public key cryptography solves that you probably use every single day. How can you create secure communication over an insecure channel between two people who have never met or shared a secret key? And if you actually think about that for a while, it's kind of amazing that it can be solved. And there's actually lots of solutions. All right, so let's talk a little bit about the history. So the first publicly disseminated solution to this problem was given a little while after the appearance of the Diffie-Hellman paper by Rivest, Shamir, and Edelman. So this is the famous RSA public key algorithm in 1978. At that time, and for some years after, the export of cryptography was controlled as a munition. So what you're looking at, the pictures that you're looking at above, up here you see a T-shirt. You don't see the part that has the RSA algorithm on it. What you see is a warning on the T-shirt. This T-shirt is classified as a munition and may not be exported legally from the United States. The shirt on the other side contained the RSA algorithm, and it was illegal to wear that T-shirt and get on a plane from the U.S. to Europe. That is a Coke can, which is a munition, which is controlled as a munition, because that Coke can also has the RSA algorithm written on it. So there was quite a bit of tension between the academic and scientific community and the government over the issue of controlling cryptography. The export controls loosened in 1998, not until 1998. And since 2009, non-military encryption exports have been reviewed by the Bureau of Industry and Standards. And so it still is true that the government is in the business of controlling cryptography and controlling what information is exported from the United States, and even what information is told to a foreign national. So now I'd like to actually try to explain some of the ideas behind the mathematics of public key cryptography. So I try to take it slow, and I won't go into too many details because I just want to sort of give you a feeling for how it might work, and then talk about some of the basic mathematics that makes this possible. Okay, so the first ingredient in a public key cryptosystem is a one-way function. A function is an input-output machine, and what we mean by a one-way function is something that's easy to do, but that's hard to undo. So it's the exact opposite of those cipher systems where we were shifting, because the shifting and the unshifting processes were the same. Easy to do, easy to undo. Now I'm talking about something that's easy to do, but hard to undo. It's like the mathematical equivalent of breaking an egg, right? Easy to break the egg. Yeah, you get it. Okay. So, what do I mean but hard to reverse? If it's easy to compute and it's hard to reverse, well, there have to be so many possibilities that I can't just go on a search and find given the input, I can compute the output, but given the output, what's the input? Well, I could go searching for it, but not if there's too many possibilities. That has to be built into this. The input is the message. The output of this one-way function is going to be the encrypted message. Okay, sounds great. All we have to do is find this one-way function. Not quite so great. If it's so hard to undo, how is my friend going to, or my stranger or the Amazon.com going to actually decrypt? I mean, if it's easy to do but hard to undo, and the answer is that this is the idea in public key cryptography, that there's going to be a secret trapdoor. And if somebody knows the trapdoor, they're going to be able to undo the function. They're going to be able to go from the output to the input. That's the hard part. It's actually not so hard to find examples of functions that at least appear to be one way, that appear to be easy to do but hard to undo. The hard part is building in this trapdoor that allows somebody out there to decrypt it. Okay, so here's the mathematical idea in public key cryptography. Everybody knows the algorithm. The algorithm is not going to be a secret. That's not how you keep secrets, by keeping the way that you keep them secret. Everybody knows the algorithm. Everybody knows what the one-way function looks like. Everybody knows what the process is. It's that possession of the trapdoor that is the sneaky part. The security of the system, therefore, does not reside in keeping the methodology secret. So if you go someplace and they say, well, we have this, your data secure, we keep it secure because we have a proprietary scheme for this. No, you need to know what the methodology is to evaluate how secure it is. Everything has to be transparent, or you can't even evaluate the quality of the security. The secret or the private key is this trapdoor information that's built in. So now what I'd like to do is try to, so here's the setup, and then I want to go back and give some examples of functions, of input-output machines that look like they're easy to do but hard to undo. So the setup in a public key encryption system is this. So everything in green is secret. That's the secret information. The red is what everybody sees. So we have Alice with her secret trapdoor information. Nobody sees that but Alice. Alice has some public information, A. Everybody sees what that is. It's a number. It's a long number. Bob has a message, a secret that only Bob can see. And he wants to encrypt the message by using Alice's public information A. So he does something to this. He forms this one-way, applies this one-way function to the message and uses A and sends off this encryption. Everybody sees the encryption. Only Alice can undo the encryption because only she knows this trapdoor. Okay, well, I mean, that's what's supposed to happen. How the heck can it happen? Well, that's what we want to talk about first, is what some mathematically hard problems might be. The mathematical equivalence of breaking the egg. Okay, so what is mathematically easy to do but hard to undo? Remember that the easy to do part will be the encryption process. The hard to undo part will be the decryption. So this is back to our Rivest, Shamir, Edelman, our RSA example. So prime numbers. Prime numbers are numbers that are divisible only by themselves and 1. let's start going through the prime numbers. Well, 2, 3, 5, 7, not 9. That's divisible by 3. 11, 13, and so on. Actually, the prime numbers go on forever, but it's not obvious. But they do. Euclid figured that out. So we have these prime numbers, and they go on forever, so they can get pretty big. They can just keep going. Now, I claim that a one-way function, the following is an example of what looks to be a one-way function, something that's easy to do but hard to undo, multiplying two prime numbers together that are really big. Let me give you a small example. I give you the number 3289, and I tell you that I've multiplied two prime numbers together to get it. How could you find out what those numbers are? What would you do? If someone gave that to you as a problem, and let's say there was a cash prize attached to it, so you actually got motivated to do it, how would you actually solve that problem? How would you find the prime factors of 3289? Just start working through every one. Well, you can skip 2 since it's not an even number. So you'd say, well, let's try to divide 3 into it, and then you skip 5. Try to divide 7 into it, and so forth. So you just keep trying. And you don't have to make too many tries before you get up to 37, right? So that's not so hard. So the problem only becomes hard when the prime numbers involved are really big. I can't resist taking this moment to advertise this wonderful poster that illustrates prime factorization by a colleague of mine, Rich Schwartz at Brown. Isn't that, you can't really see how beautiful that is until you see it on his website. But that picture represents 2, right? And that picture represents 5. And there we are to 2 times 5. And there's, let's see, there's 2 to the 5th power. Pretty cool. Anyway, we'll move on. Just wanted to show you a pretty picture. Okay, so here's a bigger example of what I was talking about. That's a large prime number. Go ahead, factor it. Okay, in case you're curious, those are the factors. So you start to imagine, then you think to yourself, well, maybe there's a sneakier way of factoring. And there are, tricks to making factoring go faster, but it's still a pretty hard problem. Okay, so RSA built the first practical public key crypto system sort of around this idea. Now, in fact, the factoring problem itself has no known trapdoor. Can't just use that as your one-way function. So they had to be a little more clever. They used this idea that multiplying 2 primes together to get another prime was a hard thing to undo, but they had to build a different one-way function. They had to find a different one-way function that actually had a trapdoor. As I said, that's always the hard part about this story. And in the RSA system, like in every public key crypto system, everyone knows the protocol, and we assume that anything sent over the internet is publicly accessible and that only the intended receiver can decrypt it. So the next slide, I'm going to show you basically how the RSA algorithm works, but I don't really expect you to look too carefully at what's here on the screen. The only thing I want you to be aware of is that in the algorithm, you have some really big numbers exponentiated by some other really big numbers. And so the RSA algorithm is really pretty computationally intensive. And how to find that trapdoor requires a little number theory. Let me tell you about Diffie-Hellman key exchange. Remember I said they came away with this algorithm for how 2 people could shout at one another across a crowded room and walk away with a secret that nobody else had? Let me explain the idea there. We're going to pick a prime number, much bigger than 5, but I'm going to just use 5 as an example right now. And then pick another number that's smaller, in this case 2. So we're going to pick 5 as a prime number, we're going to pick 2, and now we're going to start computing the powers of 2 and take their remainder. So how does that work? 2 cubed is 8. When we divide 8 by 5, we get 3 left over. So that's the remainder. So what does that look like? So 2 to the first power is 2. 2 squared is 4. 2 cubed, we said, when we divide and take the remainder, is 3. And how did I get 1 there for 2 to the 4th? 2 to the 4th is 16. Divide by 5 leaves a remainder of 1. This list of numbers gives you all of those numbers up to 5, right? 1, 2, 3, 4, but just not in that order. It gave us 2, 4, 3, 1. But it gives them all there. Okay, so when that's possible, here's the kind of picture that you get when you take a prime number and you take another number and you start raising it to powers, and then you divide by that number and just take the remainder. So for example, here I've got 60. So these numbers represent the power. 627 raised to the power 60. When I take the remainder, it looks like it gives me about 130, something like that. But what if I just pick this dot and I said, where did it come from? If you don't have this chart, you wouldn't be able to go down and say, oh, that looks like it came from about 182. In other words, this looks pretty random. It looks pretty randomly distributed. So if I just gave you a number and said, what was the exponent, you'd say, well, I don't know. Without a chart like this, I can't tell. But you can't make a chart like this if the numbers are really, really huge. So that was the basic problem behind the Diffie-Hellman. They used the fact that these powers look very random to build this secure key exchange. So in a public key cryptosystem, underlying every public key cryptosystem is a hard problem. And in RSA, it was integer factorization. In the Diffie-Hellman problem, it was this problem of finding the exponent. That's called a discrete logarithm. And there are other ways of building hard functions. And they build different cryptosystems. And to do this, we need some more hard problems. So now I'd like to talk about, this is a good one, subset sum problem. It seems simple. I give you a list of numbers, a finite list of integers, like, 3, 5, 20, something like this. And then I give you a number, and I say, I've added some of these numbers together to get this. Question, what was the combination of numbers I used? Like, for example, there's my list of numbers. There's my sum. What numbers did I use to get that sum? How would you figure out what the possibilities were? Well, you could try them all, I guess, right? You could say, well, there's 10 numbers on the list. Let's try every possible way of adding them together and see which ones give us that sum. If you have to try every one, how many tries do you have to make? Well, let's see. 12 may or may not be in the combination. So it's 0 times 12 or 1 times 12. 18 may or may not be there. 21 may or may not be there. So how many possibilities are there? 2 times 2 times 2. So there's 2 to the 10th different possibilities you have to try. Well, that's not so bad. It's only 1,024 possibilities. Well, you could do it, right? with a computer, with a calculator. But what if you have a really longer list of numbers? Like suppose I say, okay, now I've got 80 numbers. How many possibilities do you have to try? 2 to the 80? Let's see, that's about 10 to the 24. Let's look at some examples of numbers to see just how big that number is. How big is that number? Let's see, the age of the universe is about 10 to the 17 seconds. And it contains about 10 to the 22 stars. So this is 10 to the 24 is a really big number. You're not, in your lifetime, going to be able to try all those possibilities, even with a computer. Okay, so that's an example of a function that looks like it's easy to do and hard to undo. And there was a cryptosystem that was built around that. But it turned out that it was breakable, because the sneaky way they had of building in the trapdoor just didn't work for practical instances of it. So now I want to tell you a little bit about my entry into this field, which had to do with lattice-based cryptosystems and NTRU in particular. And so as Fidel mentioned, in collaboration with two of my colleagues, we had this scheme for a public key cryptosystem. This was actually initially a scheme of Jeff Hofstein, and Joe Silverman and I helped develop this over a couple of years. And it was announced and presented at the Crypto Conference in '96. And the Crypto Conference in '96 has invited papers, and it also has what's called a rump session. And they give you like 2 minutes to present your idea, or 4 minutes to present your idea. So we were at the rump session with this, 4-minute, look at this great crypto system. And after the patent was awarded in '99, and we started this company that was incorporated in '99 to commercialize, to develop and commercialize the IP. There's a long story here that I don't have time to tell you, but you'll notice the timing. I mean, this is about the middle of the dot-com bubble, which we rose to the top, and then, of course, it crashed. And anyway, the company survived and went on to build a digital signature scheme with the help of two other cryptographers, Halgrave Graham and William White. And the crypto system and the digital signature scheme has been investigated over the years by lots of other cryptographers. So we had this company, and at some point, it had 30 employees, and at some point it had 10 employees. And this brings us back to the question that I asked earlier at the beginning, which was, so how do you make a living in math? Well, of course, you're all familiar with the teaching model. I mean, this is the way people think that most people make a living in math. But in fact, lots of small companies need mathematicians. Even when our company only had 9 or 10 employees, not including us, there were still 2 PhD mathematicians on the staff. Large companies employ mathematicians, and some large companies have research divisions as well. Governments, national labs, the National Science Foundation, the National Security Agency employs hundreds of mathematicians. DARPA, many other acronyms. In fact, any industry with security and privacy issues needs mathematicians at every level. Communications, healthcare, shipping, hardware, software, social networks, finance, any industry that needs to keep data secure or that needs to make secure communications needs mathematicians. So in just 5 more minutes, I'm going to try to explain a little bit of the different other new problem that NTRU is based on. So I'm going to introduce another term, a lattice. Now, a lattice is not too hard. It's just a collection of dots, right? The red dots are what makes up a lattice. There's just an orderly array of dots. And every lattice is generated by arrows. See these arrows? And now if I just start taking these arrows, and I don't let them change, they have to stay in their same orientation, and I just add them or I add them this way, or sometimes I could subtract them. So if I add and subtract these arrows, I'm going to get all this array of dots. So this lattice is generated by these two arrows. If I just have these two arrows, I could draw the whole picture of this lattice. I could draw all these dots. So the dots can be generated by adding and subtracting the multiples of these arrows in two-dimensional space. And there's actually lots of possible pairs that generate the same collection of dots. Not so obvious, but it's true. And these generating arrows are called a basis. So here's another picture in 2 dimensions. It's a little bit smaller. So there's one arrow, there's the other arrow, and they just, if you add them or subtract them, you'll get this collection of dots. That's your lattice. Now I'm going to show you what's called a good basis and a bad basis, a good pair of arrows. This pair of arrows generates the same collection of dots as this pair of arrows. That's it's not too easy to see that you can get all these dots by adding and subtracting these big green arrows there. But it's really true. You'll get exactly the same collection. You have to go way, way out and then start subtracting to get some of these dots. These arrows are really good because you can see right away how it lays out along the grid. These arrows are not so good. They're not very, they're long, they're not very perpendicular. It's really hard to see how it generates the whole lattice. So this is good, and this is bad. But it gives you the same collection of dots. So now I'm going to tell you about this one-way function and the hard problem associated with lattices. You pick a point at random in space, and I want to find the closest dot. Right? How hard can that be? I'm just going to go in my example, I'm going to pick a point in space, and I'm going to say, what's the closest lattice point to it? Let's look at a picture. I mean, can't you just draw the picture and solve the problem? Let's see. There's my point in space. What's the closest dot? How would I find it? Well, I just draw the boxes. I just follow my arrows until I get a box that surrounds the point, and then there's the closest one. Not so hard, right? Just draw the picture. But what if the arrows I started with were the bad ones, and I tried to draw the box using those arrows? Then the corners of that box wouldn't be the closest point dot to that point in space. So the reason I could solve the problem before, just by drawing a picture, was that I was working with good arrows. But when I'm looking at this picture and I just have these bad ones, drawing the picture isn't going to find that closest dot. So you need a good basis. Good means that the arrows are short. Well, so how hard is it to find short arrows? And it's not at all hard in 2 dimensions. It's really hard in 1,000 dimensions. And that's what NTRU does. It uses that hard problem in an efficient way to build a one-way function. A function, something that's easy to do and hard to undo. So essentially, the message is a point. It's one of the dots in the lattice. And the encrypted message is a point in space. And the trapdoor is the secret good basis that allows you to find that closest point. Okay, here's some last questions. Well, that I just didn't have time to address tonight, but they're really very interesting. How do we know that these public key crypto systems that I've described or started to describe tonight, like RSA, I didn't even talk about elliptic curves, or NTRU, or how do we know that they're really secure? Just because we can't think of how to break them. Actually, that's the answer. That's actually how you know that they're secure. Because nobody can think of how to break them. It's like, can you imagine going to your teacher, your high school teacher, and saying, this problem is too hard, it was unfair, you should never have had it on the test. And the teacher says, how do you know? And you say, because nobody could solve it. Well, is that a good argument? It depends on how big the class is, right? If the class is 2 people, then maybe it's not such a good argument. But if there's 100 people in the class and nobody can solve it, then maybe it is. So that really is the argument about what constitutes security for some of these practical crypto systems, including RSA, that nobody has thought of a way to break this, even though they've been trying and trying for many years. And finally, another question that I didn't even get a chance to talk about, but which is the next generation of questions in cryptography, is what does all this mean when we have quantum computers? Thank you.
Would you be willing to answer a couple of questions?
Absolutely.
Are there any questions? Anyone? Oh, there's one way up there. Go ahead. Shout it out.
Sorry, something was happening to my mic when you were talking, so I didn't actually hear your question. Can you try it again?
Was the original intention of the the RSA algorithm, the PKCs, was that computer-based? Because if it happened in the late 70s, wouldn't be all the internet purchases have happened 10 or 20 years later?
Well, yeah. So the fascinating thing is that the RSA crypto system was described mathematically and available before the need arose. And so this is one of the wonderful things about mathematics, is that it's often there, ready and waiting when the problem appears, but it's not always out there. It's not always done to target a specific problem. So yeah, the fact that it could be practically implemented and it needed to be was something that came much later after the invention. That's a good question. Thanks.
Oh, there's a question.
You said there's no way to really tell how secure these systems are, so how do you compare the security of one system over another?
Well, assuming that there isn't some, okay, so the assumption about RSA and about NTRU and so forth is that the only way to solve them, I mean, this is the working assumption, the only way to break them is to break that problem, to break the factoring problem, or to break the closest vector problem in the lattice. And once you make that assumption, which is not provably true, it's not provably true that that's the only way to break them. But once you make that assumption, which you have to take on faith, then you can discuss how secure these particular instances of hard problems are, just as a mathematical problem. And you can say how much, how difficult it is to factor two numbers depending on the length of the keys. How difficult is it to run an algorithm to find the shortest vector in a lattice, depending on certain parameters. So it's not an easy thing to do. But you have to make certain assumptions that you can't prove in order to get started.
Question over there.
How do businesses buy and pay for encryption systems?
How or why?
No, I know why.
Well, so an encryption system is built into your computer. Your browser automatically will use a public key crypto system when you are communicating securely with your bank or with a manufacturer or something. It's just built into the operating system. Now,
so like Microsoft would have bought the encryption system or created it?
right. So a licensing fee would have been paid to RSA or to Certicom for the use of their algorithm that was patented in this particular instance.
One last question maybe up there.
Why do businesses need massive encryptions like right now too, if like they already know like the RSA thing and stuff, if those have already been made and invented, the different encryption codes, why do businesses still need mathematicians?
Well, because people continue to think of sneaky ways of attacking these things and finding weaknesses or flaws or ways to get around the implementation of them. So you can have something that's mathematically secure, but if you don't implement it correctly, then it doesn't really matter. So you've got a secret password, for your bank account, and you put it on a post-it and tape it to your computer screen. Well, it's and also this is really what happens with security. Security is compromised not by breaking the mathematical system so much as doing other things that are insecure. You'll hear about credit cards that are being released, numbers that have been released into the public, and that's generally because the credit card numbers were sent encrypted and then decrypted and stored somewhere in a garage or broken. So, but mathematicians and cryptographers are constantly working on new ideas for crypto systems and also for breaking others. And so you have to keep up with what's going on. Also, RSA no longer remains a practical crypto system if quantum computers come along.
Okay, so thank you again. If you need me to